In this video, we're going to talk about the consequences of A equaling A transpose. Now, we know the following. If B is obtained from A by interchanging rho I and rho J, I not equal to J, of A. We know that if this is true, then the determinant of B is negative the determinant of A. But now we need to look at this a little bit more clearly. The determinant of B is the determinant of B transpose equal negative. Now, this is equal to the determinant of A is the determinant of A transpose. So these two are equal. That is, this equal sign is valid. That is, B transpose is equal to negative A transpose. Well, if B was obtained from A by interchanging rows I and J, well then B transpose is obtained from A transpose by interchanging columns I and J of matrix A transpose. That is, this theorem, or this fact right here, that these two are equal, I can always go back and say columns. Okay, column I and column J. If matrix B is obtained from matrix A by interchanging column I and column J of matrix A, then the determinant of B is equal to the determinant of B transpose. So I could replace rows with columns. If matrix B is obtained from matrix A by multiplying rho I of A by S, then the determinant of B is S times the determinant of A. Now let's look at this more closely. S times the determinant of A is S times the determinant of A transpose, and B is the determinant of B transpose. So I just wrote different ways of writing those two. So that last line will be equal. And now, what is going on here? If matrix B is the same as matrix A, except rho I was multiplied by S, then matrix B transpose is nothing more than matrix A transpose, where column I is multiplied by S. That is, I can cross this out and put column I. And I don't have to reprove it. Why? Because this theorem tells me, yep, it's true. It's true. Whatever, that theorem on the top, it says that whatever is true about rows must be true about columns. If matrix B is obtained from matrix A by adding R times row I to row J, then the determinant of B and the determinant of A are actually equal. But we also know that their determinant of B is equal to the determinant of B transpose, and the determinant of A is equal to the determinant of A transpose. So these two are equal. This equals this, which equals this, which equals that. So then, yeah, those two are equal. Now, what can we talk about with respect to B transpose and A transpose? Now, all we know is that we got B by taking A and adding R times row I to row J. Now, in the transpose, B transpose is going to be the exact same matrix as A transpose, except that R times column I is added to column J. R times column I is being added to column J. And if you want to see this, if we have matrix A, B, C, D, E, F, G, H, I, and this is matrix A, and we get B by multiplying this by R and adding it to row 3. So A, B, C, let me use a little bit more space. A, B, C, first row's gonna stay the same. Their second row is not changing, but the third row, well, is R times the second row plus the third row entry, R times the second row plus the third row, and R times the second row, in this case, plus I. Now, that is A and B. Well, A transpose, now notice, please, that, again, how did I go from A to B? I multiplied the second row by R, and I added it to the third row, and that became the new third row. Now, for A transpose, the first row, ABC, becomes the first column. The second row, DEF, becomes the second column. The third row becomes the third column. Now, let us look at B transpose. The first row, ABC, becomes the first row. The second row, the first row became the first column. The second row, DEF, becomes the second column. And the third row, RD plus G, RE plus H, RF plus I, it becomes the third column. Now, if you notice, if you multiply the second column by R, you'll get DR let me just write it the other way. You'll get RD, RE, RF, and if you add on the third row, GHI, what you're going to get is RD plus G, RE plus H, and RF plus I. Look at that. That's exactly what we got. You're just tilting the matrix, the matrices, it's still going to follow. Any theorem that you can say about the rows of A or A and B, you can say the same about the columns. If A has a row of zeros, then the determinant of A is 0. Well, we know, so we know that the determinant of A transpose equals the determinant of A, which is 0. But now let's look at this carefully. If row I has all zeros for A, then column I is going to have all zeros on A transpose. Okay, so we don't even have to say this. We can just go, well, actually, I guess we do. But it makes complete sense that, so based on this theorem, based on the fact that this equals 0, and A has a row of zeros, then A transpose has a column of zeros, and the determinant is 0. Any fact about rows, when it comes to determinants, are true for columns. If you have a row of zeros, then if A has a row of zeros, then A and A transpose equals 0, and A transpose has a column of zeros. We know this fact. If A has two identical rows, then the determinant of A is 0. But check this out. Then A transpose has, then A transpose has two identical columns. And A transpose is equal to A, and since A has two identical rows, it equals 0. That is, A transpose, the determinant of A transpose is 0 whenever A transpose has two identical columns. And if you don't believe that, that this statement is true, well, suppose A transpose has two identical columns. Then A has two identical rows. And rigorously, we showed two things. We showed that A transpose equals A, and if A has two identical rows, it equals 0. We showed that. So the determinant of A transpose is 0. If A transpose has two identical columns, then A has two identical rows, and we know regardless of anything about A, whether it has identical rows or not, the determinant of A transpose and A are the same. And since A has a row of zeros, since A has two identical rows, its determinant is 0. So, the determinant, in particular, the determinant of A transpose equals 0. But that's what I wanted to show. Any statement that is true about determinants and matrix A, let me say it correctly, any statement that is true about the rows, let me try it one more time. Any comment about the determinant of A with respect to the rows is going to be valid for the same statement where you replace rows with columns. We have a statement here. Actually, we don't even have to say transpose. I think I botched that up. If A has two identical rows, then the determinant of A is 0. Well, then you can say columns. Now this won't be true, but if A had two identical, let's say 3. If it happened to be true that if A had 3 identical rows, then the determinant of A was 10. Then if A has 3 identical columns, then the determinant of A is 10. Okay, and the reason is, this is not true, but here's the logic. If A has 3 identical columns, I'll say rows, therefore the determinant is 10. But we know that two things are true. That no matter what, the determinant of A and the determinant of A transpose are equal. Okay, so this also equals 10. Because if this equals 10 and it equals this, then those two are equal. Okay, so we now know that the determinant of A transpose equals 10. But why is the determinant of A transpose equal to 10? That's because it has 3 identical columns. If A had 3 identical rows and that made it equal 10, and then A transpose will have 3 identical columns, and its determinant will also equal 10. That fact isn't true. But the logic is any statement that you can say about determinants and rows, you can say about determinants and columns. That's what I mean to say. Any statement that you can say about determinants and rows, you can say the same statement about determinants and columns. That completes this video. If you like videos like this, subscribe to my channel. Tell your friends and enemies and classmates and teachers about my channel. Subscribe to my channel. Most of all, watch and learn. See you in the next video.